Hello everyone and welcome to another lecture in Calculus 2. Today we're going to be doing derivatives of inverse trig functions. And to start off with, well, let's see, what function do we usually think of first when we think of trig functions? Probably sine. So we'll start off doing the derivative of inverse sine. The problem that I face here is that I don't really know much about the inverse trig functions. Trig functions, I can think of them in terms of opposite over hypotenuse and so forth and so on. I know very little about inverse trig functions except that essentially on a certain interval they undo a trig function through function composition. So I'll tell you what I'm going to do first of all. I'm going to give this a name. I'll call it y. I want to know the derivative of arc sine of x, which is the same thing as knowing the derivative of y. We gave inverse sine or arc sine a name. We called it y. And I'm not trying to overstate the obvious, but since y and arc sine of x are the same thing, if we find the derivative of y, dy dx, we will have also found the derivative of arc sine of x. And this sounds about as insightful as me saying that, you know who's buried in Grant's tomb? You're not going to believe this. Ulysses S. Grant. Who would have thought? It seems like I'm overstating the obvious here, but I'm not. Because it's going to turn out that in our computations, when we're looking for the derivative of this thing, it just may happen that in our computations, this may pop up, perhaps unexpectedly. But when it does pop up, we want to look at this thing and say, aha, this is what we're looking for. This is the same thing as derivative of arc sine. So we want to keep that in mind. If we find dy dx, that'll be the same thing as us finding the derivative of arc sine of x. Now let's make another observation. What does this mean? In words, what does this mean? Y is the angle whose sine is x. That's what this means. Y is the angle whose sine is x. And in terms of right triangle trig, what is the sine of x? opposite over hypotenuse. So I'm going to draw a triangle that depicts this relationship. Sound familiar? Here's my right triangle. Here's my angle Y. Y is the angle whose sine is X. So the sine of Y equals X, and X is opposite over hypotenuse. So I can make the opposite and the hypotenuse anything that I want, just as long as they are in the ratio of X to 1. See, opposite over hypotenuse, X over 1, that's X. The sine opposite over hypotenuse is X over 1, which is X. Now, could I have done this? Could I have said opposite over hypotenuse is X squared over X? Yeah, because they're still in the ratio of X to 1. Now, there's no need for me to do this. I'm just complicating things a little bit if I do this. I could do it, but I like to keep things as simple as I can. So I'm going to make the opposite side X and the hypotenuse equal to 1. So here's my opposite side, which is X. Here's my hypotenuse, which is 1. The only thing that I don't have is the adjacent side. So I'm going to compute that right now. Remember that opposite squared plus adjacent squared is hypotenuse squared. That's just Pythagorean's theorem. And adjacent is what I want. So we have adjacent squared equals hypotenuse squared minus opposite squared. And adjacent equals square root of hypotenuse squared minus opposite squared. And hypotenuse, the hypotenuse is 1. So the hypotenuse squared is 1 also. The opposite is X. So the opposite squared is X squared. Here's my adjacent, square root of 1 minus X squared. I'm going to put that down here on my right triangle. And I am now poised to do all sorts of really good stuff. I beg your pardon, just had to take some time out to clear off the board. It was getting cluttered. Now let's get back to what we really want to do. This is what we're looking for, the derivative of arc sine of X and recall also that we made y equal to the arc sine of X. Or equivalently, sine of y equals x. Well, why did I write things in terms of sine of y when I'm looking for the arc sine of x? The answer is exactly what I said in the beginning. I don't know anything about the arc trig functions. I don't even know anything as far as the geometric things that are associated with the arc trig functions. I don't know any calculus about arc trig functions. I don't know anything. I do know something about the trig functions. I know some trigonometric relationships, right triangle trig, that have to do with trig functions. And I know the derivatives of trig functions. And because I know something about trig functions, I've taken the original relationship and written it in terms of trig functions rather than inverse trig functions. Now, for some reason, maybe I'm just groping in the dark, I don't know. Since I'm looking for derivatives, I'm going to compute the derivative of both sides of this equation. The left side's pretty easy. The derivative of x as a function of x is just 1. Now over here, note that these two variables are different, which means that not only do we regard y as a variable, we regard it as a function of x. So sine of y is really a function evaluated at a function. It's a composite function. And when we compute the derivative of a composite function, what rule do we use? Yeah, that's right, the chain rule. So here's what we're going to get. If we label the sine as being the outer function and y being the inner function, we're going to get derivative of the outer evaluated at the inner times the derivative of the inner. That's the chain rule. Derivative of the outer evaluated at the inner times the derivative of the inner. Here's the outer. Sine evaluated at something. The derivative of sine of x is cosine of x. So the derivative of sine evaluated at something is cosine evaluated at something. Here's the derivative of the outer function. And now we have to evaluate it at the inner function, y. And then because of the chain rule, we have to multiply by the derivative of the inner function. Okay, let's recap our results. 1 equals cosine of y times dy dx. Okay. Now what do I do? This is where I got to pay attention and make sure that I haven't fallen asleep. What the heck do I do with that? Didn't we say at the beginning that if we find dy dx, that's the same thing as finding the derivative of arc sine of x? Holy moly! Let's not miss this. This is the thing we've been looking for. This is exactly the same thing as the derivative of arc sine of x. But holy moly, how are we going to find it? It's in an equation, isn't it? The right side is cosine of y times dy dx. This is one of two factors that make up the right side of the equation. To find dy dx, we just have to multiply both sides by cosine of y. Well, wait a minute. Is it that simple? The derivative of arc sine of x equals 1 over cosine of y? Not quite. We started out looking for the derivative of arc sine of x. It's a function of x, which means that we want our answer to be a function of x. So we're not done yet, but we're real close. Here's where we left off. Dy dx, this is what we want. This is the derivative of arc sine of x. And we have it as a function of y. We want it as a function of x. Well, what is y? Y is the angle of this right triangle. And what is the cosine of y? The cosine of y is going to be the adjacent over the hypotenuse. And if I write that a little bit more simply, that's hypotenuse over adjacent. Hypotenuse is 1. Adjacent is square root of 1 minus x squared. And dy dx, that was derivative of arc sine of x. I am going to wrap this up and put a bow on top. This is the derivative of arc sine of x. And something that you may find interesting, I found this interesting and perplexing. Arc sine or inverse sine of x is a transcendental function, but it has an algebraic derivative. And you know what? That's true of all of the inverse trig functions. all of the inverse trig functions or transcendental functions, they all have algebraic derivatives. Just one of the little things that make mathematics so interesting. Now, let's make allowance for the chain rule here. Let's suppose that u is some function of x. So we have inverse sine evaluated at a function of x. That means that this is a composite function. Here's the outer function, here's the inner function. The chain rule says we get the derivative of the outer function, 1 over square root of 1 minus the inner, times the derivative. I'll tell you what, I'll do this a little bit better. We get the derivative of the outer, 1 over square root of 1 minus something squared. That's the derivative of the outer, evaluated at the inner, u, times the derivative of the inner. Allowing for the chain rule, this is the formula for the derivative of inverse sine. Now, maybe we should do one more of these. Maybe we'll do inverse tangent, okay? Our next goal, compute the derivative of the inverse tangent of x. And we don't know anything more about inverse tangent of x than we knew about inverse sine. So what we're going to do is we're going to rewrite everything in terms of the trig functions instead of the inverse trig functions. We'll give arc tangent a name. And we'll make the observation, if we find dy dx, we will have found the derivative of arc tangent. And this makes a lot more sense than when we said if we find dy dx, we'll find inverse sine. Because now we sort of have an idea of how we're going to proceed. Y is the inverse tangent, so if we find the derivative of y, that means we found the derivative of inverse tangent. And y equals arc tangent x. What this means is y is the angle whose tangent is x. So let's draw a right triangle that depicts this relationship. Here's the angle y. Tangent of y is equal to x. And the tangent is the opposite over the adjacent. We can make the opposite over the adjacent anything that we want to make them, as long as they're in the ratio of x to 1. The easiest thing to do is to make the opposite equal to x, the adjacent equal to 1. We don't have the hypotenuse, but we can get it. This is a right triangle, so the hypotenuse squared is equal to the adjacent squared plus the opposite squared. And if I take the square root of both sides, that means hypotenuse is equal to the square root of adjacent squared plus opposite squared. The adjacent is 1. The opposite is x. So the hypotenuse is the square root of 1 plus x squared. Okay, let me clear up the board. Okay, here's where we're at. We have the right triangle that depicts the relationship y equals arctangent x, or equivalently, x equals tangent of y. And we're looking for the derivative of arctangent x. We could compute the derivative of this equation to get the derivative of arctangent x. But again, we don't really know how derivatives of inverse trig functions work. We don't have much intuition there. Even geometrically, we're not sure what significance to attach to inverse trig functions. So instead, we're going to work with this equation because we do know something about the geometry of trig functions. We do know something about the derivatives of trig functions. So I'm going to compute the derivative of both sides with respect to x. Okay. The left side looks easy enough. The derivative of x with respect to x, that's 1. The right side, notice something, please. These two variables are different. And what this means is, not only do we regard y as a variable in its own right, but since these two variables are different, we also regard y as a function of x. So what we're looking at here is a function evaluated at a function. It's a composite function. And that means that we have to apply the chain rule. Tangent is the outer function. Y is the inner function, and the chain rule says that we get the derivative of the outer evaluated at the inner times the derivative of the inner. If you don't know that from Cal 1, that's pretty easy to remember. We just walk around for a couple of days, and I'm not joking. About 10 or 20 times a day, we say derivative of the outer, evaluated at the inner, times the derivative of the inner, derivative of the outer, evaluated at the inner, times the derivative of the inner. The outer function is tangent of something. The derivative of tangent of x is secant squared x. The derivative of tangent of something is secant squared of something. So here's the derivative of the outer function. And we're supposed to evaluate it at the inner function, which means we take our inner function y and plug it in there. And now we have to multiply by the derivative of the inner function. The derivative of y with respect to x is dy dx. There we have it. This gives us 1 equals secant squared y times dy dx. And we look at that. Hey, we're a quick study. We know what it is we're looking at here. Dy dx, this is what we want. It's what we want. So I'm just going to divide both sides of this equation by secant squared y. And I got dy dx. By the way, what is secant? Isn't secant 1 over cosine? And so secant squared is going to be 1 over cosine squared. This is 1 over cosine squared. Are we done yet? No. We wanted the derivative of tangent inverse of x, which means we want our answer in terms of x. We have our answer in terms of y. We're not quite done yet, but we're real close. Okay, we're back and we're about to wrap this up. Here's where we left off. Dy dx is cosine squared y. And let me just take what might seem to be an unnecessary step. But I'll write that as cosine of y squared. And what is cosine of y? Adjacent over hypotenuse. Adjacent is 1. Hypotenuse, square root of 1 plus x squared. We square the numerator, square the denominator, and bingo, we have it. dy dx, we found it. And this was the same thing as the derivative of arctangent x. Oh my goodness. Again, we have the derivative of a transcendental function that has an algebraic derivative. Very interesting. Now, let me rewrite this formula, making allowance for the chain rule. Suppose that we have arctangent evaluated at a function of x rather than just x. That makes this a composite function. And what that means is that we're going to get the derivative of the outer function, 1 over 1 plus something squared. This is the derivative of the outer function. We evaluate it at the inner, and then we multiply by the derivative of the inner function. So making allowance for the chain rule, derivative of arctangent u, 1 over 1 plus u squared, times du dx. Now I'm going to do a summary of the derivatives of all of the inverse trig functions. Here they are, the derivatives of the inverse trig functions. There are 6 of them. We have to memorize all 6, but it's not nearly as difficult as you might think. Notice that the only difference between the derivative of arc sine and arc cosine is that to get the derivative of arc cosine, you take the derivative of arc sine and put a negative in front. The same thing is true with the derivative of arctangent and arc cotangent. Whoops, I ought to be struck dead for that. Arc cotangent of u. The only difference between the derivative of arctangent and arc cotangent is the negative sign out in front. To get the derivative of arc cotangent, we take the derivative of arctangent and just put a negative sign in front. And to get the derivative of arc secant, you guessed it, to get the derivative of arc secant, we take the derivative, to get the derivative of arc cosecant, we take the derivative of arc secant and put a negative sign in front of it. So really, there are only 3 derivatives to memorize here. And we realize that in order to get the derivatives of the arc cofunctions, arc cosine, arc cotangent, arc cosecant, to get the derivatives of the arc cofunctions, we just take the corresponding arc trig functions and put a negative sign out front. Here they are. Yes, we do have to memorize them. Take a good look. Let's get down to brass tacks now and do some good examples. Derivative of arc sine of e to the x. Let's recognize what this really is. It's the derivative of arc sine of u, where u happens to be equal to e to the x. And we know what we're supposed to get because we've memorized our derivatives. We're supposed to get 1 over square root of 1 minus u squared times du dx. Okay, we know what u is. U is equal to e to the x. Just fill in the blanks. But fill them in with black pen. 1 over square root of 1 minus u squared, where u is e to the x, times the derivative of u. Well, e to the x is that function that is its own derivative. Du dx, that is e to the x. If you're doing this on a test, I don't mind if you stop here. If you're doing this on a test, you might just want to stop here and go to the next exercise. If you're doing this for homework and you're trying to make your answer match the solution in the back of the book, it's probably not going to be exactly like this. It's going to be in a different form. I'll put the e on top, and I have square root of 1 minus something. Here I have something raised to a power, and that whole thing raised to a power. What do the exponents do? Right, they multiply. So e to the x squared is going to be e to the 2x. And almost certainly in the back of the book, this is the form of the answer that they'll have. Let's do another one. Next example. Let's rewrite this in terms of u. This is arc cotangent of u, where u equals 3x squared. And let's also write down what the derivative should look like. We're supposed to get, this is one of those arc cofunction derivatives, so we're going to have a negative sign out front. We're going to have 1 over 1 plus u squared. And then by the chain rule, we're going to multiply by du dx. I'll get 1 over 1 plus u, that's 3x squared, 1 plus u squared times du dx. That's 6x. And I'll simplify this a little bit. And this 6x will go on top. If you stopped here on a test, it probably wouldn't bother me. In the back of the book, they're probably going to put it in that form. Let's do a couple more. Another goodie. Let's write down what we have here. Arc secant of u, where u is sine of x. And let's just write down du dx. We know we're going to need it. Let's write down the form that this derivative should have. It should have 1 over absolute value of u, square root of u squared minus 1. And then we multiply by the derivative of the inner, du dx. Let's fill in the blanks, everybody. Absolute value of u. U squared, that's sine of x squared, minus 1. Du dx, that's cosine of x. If you left it here like this, I probably wouldn't mind. Sine squared x Well, this sort of looks like an impossibility, but let's continue anyway. We'll put the cosine on top. And based on what we've been given, this is the answer. Somehow I have a feeling that this is going to present a problem. I should have seen that. Foresight should have told me that this was not a good idea, but no, I had to do it anyway. But if you don't see the problem, don't worry about it. It's still a good exercise to work on. Let's do one more. Let's see.